Hello, in the second video of this series, we'll be discussing Lewis structure and kinetics. Drawing out Lewis structures allows us to visualize the bonds between atoms in a molecule as well as its lone pairs. But first, in order to understand that, we need to go through nomenclature. There are several important polyatomic ions to know, and these include perbromate, bromate, bromite, hypobromite, carbonate, cyanide, oxalate, and nitrate, along with ammonium. There are general rules for naming ionic and molecular compounds, and something is ionic if it's a metal and a nonmetal, a metal and a polyatomic ion, a nonmetal and a polyatomic ion, or a polyatomic ion and a polyatomic ion. However, something that's molecular is always a nonmetal and a nonmetal. Molecular compounds are often associated with the prefixes 1 for mono, 2 for di, 3 for tri, 4 for tetra, 5 for penta, 6 for hexa, 7 for hepta, 8 for octa, 9 for nona, 10 for deca, and so on. So, for example, P4O10 would be called tetraphosphorus decaoxide, and CO is, of course, called carbon monoxide, and since we dropped the vowel from the prefix. Ionic compounds, on the other hand, typically have an IDE ending unless it's a polyatomic ion, in which case there is no name change. For example, Na2O is sodium oxide, Fe2O3 is iron 3 oxide, since Fe must be plus 3. And similarly, CrMnO46 is chromium 6 permanganate. MnO4 is a polyatomic ion with a charge of -1. Then there are binary acids, which have hydrogen with a single element except for hydrocyanic acid, and so how they're pronounced is hydroblankic acid. So HCl is hydrochloric acid, HF is hydrofluoric acid, HI is hydroiodic acid, HBr is hydrobromic acid, H2S is hydrosulfuric acid, and HCN is hydrocyanic acid. There are also oxyacids, which are polyatomic ions with oxygen, and so you have to change the ending. So if it ends in ATE, it changes to IC, and if it was ITE, it goes to OUS. So for example, H3PO3 is phosphorus acid, and HC2H3O2 is acetic acid. Moving on to Lewis structures themselves, there are 3 parts, N, A, and S, where N stands for needed, A stands for available, and S stands for shared. So for the needed number, it's 8 besides for hydrogen and helium, for which it would be 2. And A stands for the number of valence electrons, and S would be N minus A. For example, for NH3 or ammonia, there are 4 atoms, but 3 of them are hydrogen. So for N, we do the sum of 8 times 1 plus 3 times 2, and so that comes out to 14. And for available, it is 5 for nitrogen and 1 times 3 for the hydrogens, and so that comes out to 8. And 14 minus 8 equals 6, and we divide that by 2 to find the number of bonds. So in this case, there are 3 bonds, and we put nitrogen in the center, since it's generally the first atom listed. And then we can connect them, and each bond counts for 2 electrons, so there are 6 in the diagram so far, and so we need to add 2 more lone pair to the central atom. A second example is carbonate. So for the needed number, it would be 8 times 4, which is 32, and for the available number, it would be 4 for carbon and 6 for oxygen times 3, and then we're adding the additional 2 electrons since it has a charge of -2, and that comes out to 24, and 32 minus 24 is 8, divide that by 2 is 4 bonds. So in the structure itself, there's going to be 4 lines for bonds between the carbon and the oxygens. And so one of them is going to have 2, which I'll mention again later. And there's 2 times 4, which makes 8, but we need 24, and so then we need to add 16 lone electrons. And so there is 6 around each of the single bonded oxygens and 4 around the double bonded oxygen. And then finally, we're going to encapsulate this in brackets with the -2 to designate that this is an ion. And this is an example of a resonance structure where there, in this case, are 3 equivalent structures because there are 3 options for the double bond. Next up is formal charges to see stability, and so ideally these would be all zeros, which is possible if there's no charge. So the formal charge is equal to the number of valence electrons minus the sum of the number of bonds and the lone electrons. And so basically what this number is saying is how far off the baseline of stable that it is. So for example, a negative means pulling more electrons to itself. So you can adjust your structure based on this formal charge, and for example, you can pull in lone pairs to make a double bond or the other way around in order to make the most stable structure. Next up is hybridization, which relates to bonds with more than one orbital. And so we're going to be looking at electron groups from 2 to 6. So if there's 2 groups, the hybridization is sp. For 3, it's sp2. For 4, it's sp3. For 5, we're introducing that d orbital, so it's dsp3. And for 6, it's d2sp3. And based on this, there's electronic geometry. So for example, with just 2 electron groups, they are linear, since it's just a line that connects the 2 of them basically. And for 3, it forms a triangle shape, and so it's called trigonal planar. But for 4 groups, they are all spaced equally apart from each other, and so it forms a shape, a tetrahedron, so it's called tetrahedral. Then for 5 groups, it forms a shape with the base of like a trigonal planar and with one projecting upwards and another electron group projecting downwards, and so it's called trigonal bipyramidal. And lastly, for the 6 groups, there makes an octahedral shape since it's like a square planar, and then once again with the one group above and one group below. So the respective bond angles are 180 degrees, 120 degrees, 109.5, 90, and 120 and 90. And here are some basic diagrams to help visualize what I've just explained. The next thing is molecular geometry, which is similar to electronic geometry, but it differs based on the number of lone pairs there is. First, if the electronic geometry was linear, the molecular geometry will also be linear. But from trigonal planar is where things start to change. So if there is no lone pairs, it still remains trigonal planar. But if there is a lone pair, that means there's one less bond, and so it's called bent. Then for tetrahedral, once again, if there are no lone pairs, that means it's still the same. But if there is one lone pair, that means that one's removed, and so it's trigonal pyramidal, just based on the shape. And then if there are 2 lone pairs, that means it's bent. Then for 5 electron groups, once again, no lone pair, still trigonal bipyramidal. But if there is a lone pair, that it would be located in the center area where each of the bonds are 120 degrees away from each other. And so then it makes almost a seesaw shape, which is what it's called. And if there's 2 lone pair, it once again removes from there, and so it makes a T, so it's called T-shape. And if there's 3 lone pair, that means the last one in the middle extending outward is removed, and so it's linear. Then for octahedral, if there's 1 lone pair, it's taken away from the one projecting either up or down, and so it's square pyramidal. And if another one is removed, then it's from the other side, making it square planar. Another thing to consider with molecular geometry is polarity. And so this is when, of course, they don't equally share the electrons. And if it's polar, that means that the bond angle will be less than what it normally is with electronic geometry. And you can think of it as if the lone pairs are more negative, and so they force the other bonds to become closer to one another. For example, if the molecular geometry were trigonal pyramidal, we'd say that the bond angle is less than 109.5. The ones that are polar are highlighted in pink, and so that would be bent, trigonal pyramidal, bent, seesaw, T-shape, and square pyramidal. And the rest of the non-polar ones are highlighted in yellow. And the last part of this topic is the sigma and pi bonds. So the sigma bonds are because of the overlapping s orbitals, and the pi bonds are because of the overlapping p or d orbitals. And a single bond will have one sigma bond, a double bond will have one sigma and one pi, and a triple bond will have one sigma and two pi. An example is N2, so it has an N of 16, an A of 10, and an S of 3 bonds. And so we can draw in a triple bond, meaning that it is 1 sigma and 2 pi. Next up is kinetics, so it describes the motion and changes in chemical reactions. It's influenced by temperature, catalyst, state, and concentration. So for example, with a higher temperature, there's more frequent collisions and more often activation energy is met. And a catalyst lowers the activation energy, and the state of course solid liquid gas and concentration, which can lead to more frequent collisions. We're going to start off with some rate stoichiometry. So first, the rate is equal to the change in concentration over the change in time. And we have this reaction here. So the rate is equal to negative 1 over the coefficient for a reactant times the rate, once again, the change in the concentration over the change in time. And so this rate is equal no matter what part of the reaction that we use. And for the product side, it's just 1 over the coefficient without the negative sign times the rate. Here is an example for N2 plus 3H2 goes to 2NH3. And we are given that the change in time is 32 seconds, the initial concentration of NH3 is 0 molars, and the final concentration of NH3 is 1.2 molars, and we're left to find the rate for H2. And we can start off by setting up the equation. So since the rates have to equal, using H2 and NH3. And then we can plug in our known values and solve for our unknown, which turns out to be negative 0.0563 molars per second. Next is the general rate law, which says that the rate is equal to a constant k times the concentration of A raised to the n times the concentration of B raised to the m and the concentration of C raised to the p, and so on. And the units for k are 1 over m raised to the total order minus 1 times time. Here is an example problem that illustrates this. So we're given a data table with concentrations for A, B, and C, as well as the rates for experiments 1, 2, 3, and 4. And so we can compare two of the experiments so that only one concentration changes. And so we can find the proportion of the concentration in comparison to the rate. So for example, for number 2 and number 4, when dividing these, we get 0.5 raised to the p is equal to 0.5. So p must be 1, and so C must be first order. We can do the same for experiments number 1 and 3, and another way to think about it is trying to find the number that you multiply the first to get the second. And so in this case, a you multiply by 2, and for the rate it's multiplied by 4, and so that means n must be 2 and a must be second order. And now we can compare experiments 1 and 2. So it's multiplied by 1/2 and 1, and so 1/2 raised to the m must be 1 and m must be 0. Therefore, r must be equal to k times a squared times c. And we can then solve for k. So for example, using experiment 4, we have 9.20 times 10 to the negative second is equal to k times 1.3 squared times 2.2. Then solving for k, we get 0.0247. Since the total order can also be seen as the sum of the exponents, it's 2 plus 0 plus 1, and that equals 3. 3 minus 1 is 2, and so that means the units for k must be 1 over m squared times seconds. Next are the integrated rate laws. So if something has 0 order, that means that the equation would be the concentration of A is equal to negative kT plus the initial concentration of A. If it's first order, that means it's ln of A minus kT plus ln of initial A. And if it's second order, it's 1 over concentration of A is equal to positive kT plus 1 over the initial concentration of A. And so this tells a change in concentration per time. So another way to determine order is by graphing it. So using t for the x-axis and either concentration of A, ln A, or 1 over A for the y-axis. So for example, if the graph for t and 1 over A was positive and linear, then we'd know that it was second order. Next is the half-life, or the time for half of a reactant to be used up. And for the zero order reaction, it is the initial concentration of A over 2K. And for the second order, it is 1 over K times the initial concentration. But the important one is the first order, and so this is ln 2 over K. And so it's constant, and it's concentration independent, and an example of this is nuclear decay. And next is the Arrhenius equation, where K is equal to Arrhenius number times E raised to the negative EA, or activation energy, over RT, where T is in Kelvin and R is the 8.314 joules per mole Kelvin. And this can be rewritten as ln K is equal to negative EA over R times 1 over T plus ln A. And so this turns it back into y equals mx plus b form to graph. And our x would be 1 over t, and our y would be ln K. The last topic is reaction mechanisms. And for elementary reactions, it's a single step, and so it's controlled by that step. But otherwise, the rate is controlled by the slowest step. So, for example, if we had A plus B goes to C and C plus D goes to E, the rate would be K times C times D, since that's the slow reaction. But there is one problem with this, in that it involves intermediates, so specifically the intermediate C, and we typically want to avoid that so we can have better control over the outcome of a reaction. But before we jump into the example again, there's just some vocabulary to go over. So an intermediate is something that's created and then used, whereas a catalyst is used and then created. Although it never really gets destroyed, it's used up and then comes back out as it originally was. And overall reactions don't include intermediates, and usually not catalysts, although catalysts can sometimes be written over the reaction arrows. Going back to our example, for the first reaction, we know that the rate of the forward reaction is equal to the rate of the reverse. And so in other words, the concentration of A times the concentration of B is equal to the concentration of C, So we can substitute this in with our first equation, so we get R is equal to K times A times B times D. Thank you for listening.